Hi everyone, my name is Dario Pasquini, PhD student from Sapienza, University of Rome, and in collaboration with my co-authors Giuseppe Ateniese and Massimo Bernaschi, today I'm going to present you a new class of password meters that we call Interpretable Probabilistic Password Strength Meters. Let's start by giving a little bit of background. A password strength meter is any tool capable of measuring the security of a password in consideration of a guessing attack. Meters often appear in web applications and are used to guide users to choose secure passwords at composition time. The workflow is very easy. The user chooses an initial password and the meter returns a score that evaluates its security. If the password reaches some predefined security threshold, we have the password. If the password does not reach the threshold, the user is invited to change the inserted password or improve it by changing some characters. But here comes the problem. Typically, users don't know anything about how to choose a secure password. Consequently, it's very hard for them to understand why the chosen passwords are weak and how they should improve them in order to reach a secure password. Eventually, users end up choosing insecure passwords, even if these are detected as weak from the meter. Obviously, this trend reduces drastically the security of the authentication system. Therefore, to better assist the user in the composition process, password meters must rely on additional feedback mechanisms that are aimed to help the user to improve the chosen password. Currently, these mechanisms are extremely simple. For instance, a common choice is using handcrafted dictionaries of tokens to detect and notify weak tokens in the user's passwords. Here, the meter contains various dictionaries divided by semantic. For instance, we can have a dictionary of first names or a dictionary of keyboard patterns and so on. When the user composes a password that contains a weak token, the meter produces a textual message encrypted for the specific matching dictionary, explaining why the token should be avoided in the password. In a similar way, meters can implement a set of heuristic rules to suggest users methods to improve their passwords. For instance, they may propose to capitalize a letter in the middle of the string, or moving numeric patterns from the end of the password. Those can also automatically apply random perturbations on the typed password, so to improve it. For instance, they can automatically change some characters of the password with other random characters. Obviously, these simple approaches are very limited. The first main drawback is that those are able to model just few hardwired feedback scenarios. For instance, the meter can implement only a limited number of dictionaries or heuristic rules. Furthermore, every dictionary or heuristic rule must be carefully defined and implemented by human experts, making these approaches very hard to scale as well as expensive. Secondly, these methods do not rely on any rigorous security definition. That is, these are based on human intuition and domain knowledge, and we cannot be sure that these are representative of what is really secure and what is not. Additionally, those methods are not general solutions. For instance, different communities have different weak composition habits that may require different heuristics or dictionaries to be described. Adapting those solutions to different contexts will require the re-implementation of all the methods. Here comes our work. Indeed, today we are going to talk about how to create a meter capable of overcoming all these limitations. We show that it's possible to create a password meter that is both capable of accurately measuring password strength, but also capable of an intrinsic feedback mechanism that can help the user in the composition process. In contrast with previous approaches, this feedback mechanism is general, meaning that it can handle an unlimited number of feedback scenarios. This mechanism is sound, meaning that it relies on a rigorous security definition. And finally, this meter is fully data-driven, meaning that we can learn it from raw data. This is how our meter works. Instead of giving an atomic score to a password, the meter is capable of disentangle the security contribute of each character composing the password. This automatically explicates which part of an estimated password is actually making it weak or strong. In this way, users always know which parts of the password should be changed during the composition process. More importantly, such mechanism is based on a pure probabilistic reasoning, so we avoid any human effort in the process. We implement the meter using a deep neural network that can be directly learned from raw data. In the next slides, we will see how such a meter can be implemented. We start by presenting the most theoretical aspects of the model. Then we will cover the machine learning framework that implements the meter. Finally, we validate the soundness of our approach by presenting empirical results. First of all, our meter is a probabilistic password meter. This is a well-established class of meters that bases on a rigorous security definition. Probabilistic meters model an attacker who knows the distribution of the attacked passwords and performs an optimal guessing attack by issuing guesses in the decreasing probability order. Meaning that the attacker knows the probability of each password in the password space and performs the attack by trying the passwords with high probability first. Within this adversarial model, the probability of passwords directly translates in a strength score. That is, passwords with high probability are considered weak, as they will be quickly guessed from the attacker, whereas low probability passwords are secure, as they will be matched by the attacker only after many guesses. Actually, probabilistic meters are implemented via probabilistic models. These models are learned by approximating the probability distribution of an observed set of passwords, that is typically a real-world password leak. When we have to apply the meter, we use the probabilistic model as explicit probability mass function to evaluate the probability of a password, and then we derive a strength estimation from this probability. To be precise, the used probabilistic models are structured probabilistic models. Those, to perform the mass estimation, factorize passwords in a sequence of random variables, rather than evaluate them atomically. Commonly, passwords are segmented at character level, that is, each character in the string is described as a single random variable. Then, the joint probability of the full password is estimated by multiplying the probability of each assignment of the internal random variables. However, such random variables are not independent from each other, so their probability is computed in consideration of the configuration of the other variables in the string. In particular, these probabilities are controlled from so-called local conditional distributions. To make this concept clear, let's consider an example. A very good example of structured probabilistic model is an autoregressive model. This class of models appears very often in machine learning. usually under the form of recurrent neural networks. These are generally applied on data sequences, such as passwords. When we use them to estimate the probability of a sequence, we have that each step in the sequence receives a probability that is measured in consideration of all the steps that come before in the sequence. That is, the local conditional distribution of each character is conditioned to all the previous characters. And the joint probability of the whole string is defined by the product of those local conditional probabilities, one for each character. Now, our meter bases on the intuition that these values of local conditional probabilities assigned to each character are very good descriptors of the relation between the password strength and its structure. The main intuition here is that those describe how the joint probability of the string distributes among all the characters composing the password. For the password guess me, this can be easily visualized on the plot on the right, where the contribute of each character is reported in consideration of the total probability of the password. Here, each block in the bar represents the mass contribute of the character, whereas the whole bar is the total probability. Now, knowing how the mass of the password is distributed allows us to understand which parts of the password are pushing it to have high probability, so that push it to be insecure. In this example, the plot shows that most of the mass of the password is maintained from the second S in the string. Therefore, by perturbing such high probability character, we can drastically reduce the joint probability of the password. That is, we can make the password stronger. Relying on this intuition, we can build a probabilistic feedback mechanism. For instance, these probabilities can automatically detect macro components in the passwords, such as weak tokens, by assigning very high probabilities to the characters that compose them. In this way, we can simulate token-lookup approaches without the explicit use of dedicated dictionaries. In a similar way, the meter is capable of automatically describing strong composition behaviors like the ones implemented in heuristic feedback mechanisms. But there is a problem. We cannot use standard approaches such as autoregressive models to enable such feedback mechanism. In particular, the problem here is that these models assume independence properties among characters that make the local conditional probabilities not well representative. For instance, as shown in the example, the first character in the string is always assumed independent from all the other characters in the string. That is, its value is the same for each possible configuration of the remaining characters. This produces very counterintuitive results for the local conditional probability. And in order to overcome to this kind of limitations, we have to rely on a different probabilistic structured model in the mass estimation process. In particular, we based our mass estimation on an undirected and complete structured model, where every random variable is assumed to be conditioned to all the other variables via undirected connections. Here, the probability of a random variable depends on all the others. This can be clearly seen in the local conditional probabilities reported on the right of the slide. However, under this construction, the product among the local conditional probabilities do not produce a probability estimation anymore. Instead, such product results in a normalized version of the joint probability, meaning that the sum of the probability of all the passwords in the password space is not 1. Nevertheless, the normalized joint distribution preserves the core properties that are needed to the meter functionality. as the proportion among all the probabilities is exactly the same as the one imposed from the true joint probability distribution. Eventually, this new model allows us to produce suitable estimates of local probabilities. Losing the causality implied by autoregressive models, now the information among random variables can flow in any direction. For instance, now the probability of the first character of the password can be influenced by the characters that follow in the string. This allows the resulting local conditional probabilities to be representative of the actual structural importance of each character. Okay, now that our meter has been described from the theoretical point of view, we can talk about how such a meter is actually implemented. What we do is simulate the undirected and complete probabilistic model described above using a deep neural network. In particular, we rely on a convolutional autoencoder. Here, the encoder and the decoder are two residual networks, mainly composed of monodimensional convolutional layers. This autoencoder takes a password as input and produces another password as output. We train the model in an imputation task, or more precisely in a masked language modeling task. That is, during the training, for each password in the train set, we randomly mask out a single character from the input password. Then the masked password is fed into the model, which is trained to recover the masked character, basing only on the remaining visible characters. More precisely, the model produces as output a probability distribution over all the possible characters the masked character can assume. Eventually, the model is trained with a cross-entropy based loss function that measures the distance of the produced probability distribution in consideration of the correct character. This probability distribution produced from the trained autoencoder actually is nothing more than the local conditional distribution of the masked character for our undirected and complete probabilistic model. Indeed, it measures the probability of a certain character of appearing in a certain position in the password, this in consideration of all the other characters in the string. That is equivalent to the local conditional distribution of the structured probabilistic model described above. Once we have the trained network, we can use it to infer the local conditional probabilities and the joint probability of a password. In order to do that, we use the same trick used during the training. We mask a character and we query the model to infer the probability of the missing character. We apply this procedure for each character in the password. Obtaining the local probabilities, we can use this to enable the feedback mechanism. Instead, by multiplying them, we obtain the scalar normalized probability that we can use to give a global strength estimation to the password. Here it's important to note that, differently from an autoregressive model, the network inference can be computed in parallel with almost any overhead over the single inference. In this final part of the talk, we present empirical results to demonstrate that the local conditional probabilities are indeed good descriptors of password security at structural level. To this end, we measure the security improvement induced by perturbing passwords according to the local conditional probabilities. This evaluation follows 4 steps. Given a set of passwords, we perform a guessing attack on all the passwords in the set, so to estimate their guess numbers. That is, how many guesses an attacker has to perform in order to guess a specific password. Then we apply a perturbation on each password by modifying key characters of the string. And then again, we perform a guessing attack on the perturbed passwords and compute the new guess numbers. Finally, we compare the old and the new guess numbers to measure the security improvement caused by the perturbation. Here are the results. We compare two perturbation strategies. The first is a baseline obtained by choosing the characters to be substituted randomly. The second is the one based on the local conditional probabilities estimated by our meter. That is, we perturb the character with highest probability in the string. The average guess number increment for the true approaches is reported on the right, where k is the number of perturbed characters. The meter-based approach is capable of inducing a guess number increment that is an average twice than the one induced from the baseline. The result verifies that the estimated local conditional probabilities are indeed some descriptors of password security at structural level. Thanks for your attention. You can find our code in this GitHub repo.